need to understand something before we go any further. This is not speculation. This is not the pessimism of people who lack imagination or courage. The engineers who designed the Apollo guidance computer, the scientists who mapped the Van Allen belts, the physicians who documented what spaceflight does to the human body. They are not afraid of the future. They are afraid of a specific thing. A thing that has numbers attached to it. A thing with a name. The name is the problem of Mars. Let's start with distance, because everything else follows from it. At its closest approach, Mars sits roughly 54 million kilometers from Earth. At its farthest, that number climbs past 400 million. The average useful launch window, the window when the orbital geometry actually makes a trip feasible, puts the travel distance at somewhere around 225 million kilometers, a journey of approximately 7 months in a spacecraft moving faster than anything a human being could survive driving in a car. 7 months. One way. That is not the remarkable part. The remarkable part is what 7 months in deep space does to a human body, and what we have learned, specifically and measurably, from the people we have already sent there. Scott Kelly spent 340 consecutive days aboard the International Space Station. His twin brother Mark stayed on Earth. This was not an accident of scheduling. It was a controlled experiment, the most expensive biological comparison in human history, designed to isolate the effects of long-duration spaceflight by using a genetic baseline. When Scott returned to Earth in March 2016, researchers compared the brothers at the molecular level. What they found has not been fully resolved. Scott's telomeres, the protective caps on the ends of chromosomes, the structures that shorten as cells age, had lengthened during spaceflight and then rapidly shortened upon return. His gene expression had changed. His microbiome had shifted. His cognitive performance showed measurable decline in certain domains. His vision had degraded from fluid pressure changes around the brain. His DNA itself had been altered by cosmic radiation in ways that his body partially repaired and partially did not. 340 days. On the ISS, inside the protection of low Earth orbit, which sits comfortably within the magnetosphere, the planet's magnetic shield against the most energetic particles the Sun and the galaxy throw at anything moving through deep space. Mars is not in low Earth orbit. The journey to Mars crosses the full depth of interplanetary space, beyond the magnetosphere, beyond the shield, into an environment where the radiation dose is not an abstraction calculated from measurements made through a protective envelope, but a direct and continuous bombardment of galactic cosmic rays and solar energetic particles. NASA's own estimates, based on data returned by the Curiosity rover's radiation assessment detector during its cruise to Mars, place the total radiation dose for a round-trip Mars mission, transit plus surface time, at somewhere between 6 and 10 sieverts. The lifetime limit the agency sets for astronauts is around 0. 6 sieverts total, a number calibrated to a 3% increase in fatal cancer risk. That limit exists because above it, the agency has determined that the risk to the individual becomes ethically indefensible. A Mars mission, by the math, exceeds that limit before the crew lands. And we have not yet talked about the landing. The atmosphere of Mars is approximately 1% as dense as Earth's. That sentence contains everything you need to know about why landing on Mars is among the most technically violent acts in the history of spaceflight. Thin enough to heat the entry vehicle to thousands of degrees. Not thick enough to slow it down. The 7 minutes between atmospheric entry and touchdown, the engineers call it the 7 minutes of terror, and they are not being dramatic, is a window during which the spacecraft is either performing a sequence of precisely choreographed events with zero margin for error, or it is not. There is no middle outcome. Every Mars landing humanity has attempted has been a robot. Everyone has been designed to survive alone for years after arrival. Everyone has been designed to be lost. A crewed vehicle is approximately 5 to 10 times heavier than any Mars lander humanity has successfully deployed. The physics of landing something that mass on Mars has not been solved, not tested, not validated. The largest payload ever landed on the Martian surface, the Perseverance rover, massed about 1 metric ton. A crewed lander capable of sustaining a human crew and carrying enough fuel for return ascent would require landing something closer to 40 or 50 metric tons. The gap between those numbers is not an engineering challenge. It is an engineering mystery. No one has proposed a solution that has survived full technical review. The parachute systems used for robotic landers cannot scale. Retropropulsion alone generates significant dust and erosion concerns. Inflatable decelerators are promising in theory and unproven at scale. The surface itself perclorates, extreme cold, low gravity that preserves muscle loss while preventing the cardiovascular adaptation that low Earth orbit partially provides is a compounding problem. None of this means it is impossible. It means that the people who study it most carefully are the ones who say it cannot happen soon, cannot happen safely, cannot happen in any timeline that matches the announcements currently being made. Let's talk about the return. If a crew lands on Mars, they cannot leave immediately. The orbital geometry that governs launch windows works in both directions. Having arrived during one window, they must wait for the next window to open, approximately 26 months after arrival, before the orbital mechanics favor a return journey. This is not adjustable. This is not a scheduling problem. This is the movement of planets around a star. 26 months on the surface. In a habitat that must be brought from Earth, assembled robotically in advance, and remain structurally intact throughout a journey, no human system has ever been verified to withstand. Heated against temperatures that regularly drop below -100 degrees Celsius. Pressurized against an atmosphere in which breathing unprotected would kill a person in approximately 2 minutes. Protected against dust storms that can shroud the entire planet for months and can bury solar panels, clog air intakes, and structurally damage equipment designed on Earth and never tested in that environment for anywhere near that duration. And then the crew must launch from Mars using a vehicle whose fuel was either carried from Earth, adding enormous mass to the initial mission, or manufactured on the surface using processes that have never been demonstrated at scale in that environment, to rendezvous with an orbiting vehicle that has been sitting in Martian orbit for 26 months, unmaintained, exposed to radiation, thermally cycling daily, waiting. Every failure mode in this sequence kills everyone. There is no rescue mission. The round-trip communication delay at Martian distances runs between 3 and 22 minutes each way, the minimum. A crew member who has a medical emergency on the surface of Mars has, at best, a 6-minute wait before a distress call even reaches Earth. At worst, a 44-minute wait. Mission controllers cannot intervene. The crew is alone in a way that has no precedent in human exploration. Scott Kelly could talk to his family with a 0.04-second delay. A crew on Mars would watch a movie finish before they received the reply to their question. Carl Sagan spent years arguing for human exploration of Mars. He wanted it. He believed in it. He also said clearly, in multiple contexts, that the moment anyone seriously attempts to send humans to Mars, they should understand they are doing something from which the humans may not return. Not as a failure of planning, as a statement of what Mars is. There is a concept in human spaceflight called acceptable risk. It acknowledges that any crewed mission carries risk of death. The Mercury astronauts knew this. The Apollo crews knew this. The shuttle crews knew this. Gus Grissom, Ed White, and Roger Chaffee burned to death in a command module during a routine ground test. They were not in space. The ship was not moving. The risks of spaceflight had found them anyway. The acceptable risk framework works when the risk is quantifiable, when the mission has a reasonable chance of success, when the crew can return if something goes wrong. It breaks down when the radiation exposure alone violates the agency's own lifetime limits before the mission begins. When the landing system does not yet exist. When the return depends on conditions that cannot be fully controlled. When a single failure in the habitat, in the ascent vehicle, in the life support system, in the crew's health, ends the mission permanently and lethally. NASA knows this. The agency has internal documents, risk assessments, technical reviews that have been partially declassified and extensively analyzed. They do not use the word impossible. They use words like technically not ready, like significant gaps in capability, like unresolved challenges. They set target dates for crewed Mars missions that move forward in time as the date approaches, not because of budget cuts, but because the problems being identified are harder than the ones solved to get this far. There is one more thing to understand about what is being proposed. The most prominent current plans for Mars exploration do not include a robust return architecture. They include the language of one day eventually, with experience and infrastructure. They include the suggestion that early missions may be designed for permanent settlement rather than return. The framing is presented as vision, as ambition, as the next chapter. What it is, technically, is a one-way trip with a narrative placed around it. Humans have made one-way journeys before. People walked out of Africa and did not return. People boarded ships for continents they had never seen and understood they were leaving forever. There is something real in that comparison and something that fails. The people who crossed oceans found air they could breathe. They found water they could eventually drink and food they could eventually grow. They were cold and sick, and they died in enormous numbers. But the planet was not trying to kill them in every moment. Mars is not hospitable in any temporary sense that infrastructure can bridge. The pressure is not something a window can fix. The radiation on the surface, even with the thin atmosphere providing marginal shielding, accumulates in a body continuously. The soil is toxic. The distance from resupply is measured in years. A person who lands on Mars and stays there is not a pioneer in the tradition of someone who crossed an ocean. They are something we do not have a good word for. A person who has gone somewhere no rescue can reach, where the environment is comprehensively lethal, where they will die of something: radiation, equipment failure, illness, psychological fracture, simple bad luck. Years or decades before they would have died on Earth, and they will die knowing that no one is coming. That is what is being discussed, not in the language being used to discuss it, but in the numbers behind it, in the physics of the problem, in the internal assessments of the organizations who have spent the most time with the actual data. NASA has known this for years. The question is not whether we can solve the engineering. Given enough time, enough money, enough sacrifice, enough willingness to let people die trying, some version of a human being will eventually stand on the surface of Mars. That is probably true. The question is what we are asking them to agree to, and whether we are being honest with them about the answer.